The Polynomial Power Play, the Trace and Determinant Saga. Watch as two simple calculations expose the profound mysteries lurking inside every matrix's DNA. In our problem today, problem A21, the statement is, it's obvious that the trace of a diagonal matrix is the sum of its eigenvalues, and its determinant is their product. Just look at equation A79. It follows from equations 65 and 68 that the same hold for any diagonalizable matrix. Prove that in fact the determinant is the product of the eigenvalues and the trace is the sum of the eigenvalues for any matrix. The lambdas are the end solutions to the characteristic equation. In this case, in the case of multiple roots, there may be fewer linearly independent eigenvectors than there are solutions, but we can still count each lambda as many times as it occurs. Hint: write the characteristic equation in this form here and use the results of problem A.20, which is our last problem. So, in light of the provided hint, it can be deduced that the characteristic equation manifests as an nth order polynomial which is amenable to factorization in terms of its complex roots, as we see here. As a result, we can go ahead and try to expand it, but be careful with everything. We see that we know we have, the variable lambda here because anything with the subscript is a root. So lambda as a variable is in the second position with the minus sign. So we know that for n many roots, we're going to have n many powers here because of the fundamental theorem of algebra. And since this has a minus sign on it, we're going to have a minus sign on this to the nth power. Our next lowest term would be n minus 1. Again, since the negative sign's on the lambda, we have to take it with us. And then we see that we have a collection of some entities after we distribute, and these entities we're claiming are the roots. Now this over here is some collection of product of numbers that we need to actually see what they are. Of course, since we're looking at the coefficients, we could go ahead and take out the actual variable here of the polynomial. So we see that our coefficient's really just -1 to the n, -1 to the n minus 1 with all the lambda subscripts here. And then this one is the C0 since x, or in this case lambda to the 0, is not included. Now for this distribution part of this proof, I have saw a write-up or an argument using the binomial coefficients and combinatorics. So you can use the NK notation there if you want, but that seems to be a little overboard for what this page and what this proof is trying to show. But nonetheless, that would be a cool thing to kind of check out. As a result, though, when we're comparing with the results of problem A.20, we see that the leading coefficient had to be -1 to the n. We see that there. We see that the second leading coefficient, Cn minus 1, had to be -1 to the n minus 1 plus or multiplied by the trace of t. Now again, this is the trace of the matrix regardless of any type of matrix. These are specified eigenvalues for the matrix that's diagonalizable. Here is a determinant for any matrix, diagonalizable or not. Here's what we have for diagonalizable. As a result, if we compare the coefficients, so blue to blue, and then we'll do green to green, by looking at Cn minus 1, as we see here, knowing that we have this up top in the polynomial, we can set that equal to this result from A20 here, and we see that the negative ones cancel on both sides, so we're good. This tells us that the trace of t is equal to the sum of the eigenvalues. And I can't tell you how many times this concept is going to come up later in this appendix, so be aware of that. Finally, we run that through the same thing, compare the C0 coefficients we have from the polynomial up here, the product of eigenvalues, and then from A20 we have that the determinant of t has to equal C0. Therefore, we know that the determinant, regardless of any type of determinant, is equal to the product of its eigenvalues. Now, these two checks are very, very important, and when we're dealing with transformations and things like that, you're going to want to check yourself because it gets messy pretty quick. So, as a way to check our understanding of this and not just wave our hands and say, okay, that makes sense, let's go ahead and elucidate these concepts more thoroughly by using an example to actually cement what we're trying to understand. So let us revisit the matrices previously encountered in problem A8, which will serve as an illustrative case study to reinforce these concepts that we were just talking about. And what we previously found were that for a matrix B as defined here, we found in A8 that the determinant of B was 3. We can quickly find the trace of B by simply adding up the main diagonal elements. So in this case 2, 1, and 2. That equals 5, easy enough. Now be mindful that 2, 1, 2 might not be the eigenvalues because we're not diagonalized on this matrix B. As a result, what we need to find are the eigenvalues. And so we know that we need to set up our determinant equation or matrix equation or the eigenvalue equation. And that B minus lambda I, easy enough, set that up there. Again, this has to equal 0 because it must be singular. As a result, in order to evaluate this determinant, we're going to use cofactor expansion again. And so we see that cofactor signs, we have our matrix of signs here to choose from based on what row or column. And as you see from the color code, we're going to use the second row here because the second row has the most zeros, and that's where it's most convenient. Okay. Now again, with things like cross products, we see that the first row is commonly used, but that might not always be the most convenient. So as a result, we see that we have a 0 cofactor here, a 0 cofactor here, the minus plus minus structure, and then we have our subdeterminants here, here, and here. Easy enough. But with multiplying by 0, we don't care what this minor determinant evaluates to, nor this one, so get rid of them. And now we're just stuck with 1 minus lambda from that middle entry and all the components around it. As a result, expanding this, we keep this plus 1 minus lambda here, bracket up, and then we see we got this element times this element given here, minus this other cross, so negative times negative I. The negative signs cancel, then we get I squared plus I squared, so it turns to minus 1. Distribute that, all that fun stuff is in the PDF, which is on Patreon when this releases. Nonetheless, we get a factored form here, negative out front, go figure. Then we have lambda minus 1 squared, so we're going to have multiplicity there, and then lambda minus 3. Again, all that has to equal 0. So we know that our eigenvalues are 1, 1, and 3. Again, multiplicity 2 there. Since we're a 3 by 3 matrix, we need 3 eigenvalues, and we have them. That being said, now on to the properties. What we're going to need to do is to rewrite this polynomial in its expanded form as compared to its factored form. So working from this line here, after we distribute these out and simplify with this, we get this expanded form here. Now we'll distribute this factor into it, leaving us with a third degree polynomial as we would want. And now we see that the two properties we're looking at abide to the second coefficient and the last coefficient. So from problem A20, the one before us, we know that the second coefficient, which is n minus 1, so n equals 3, that leaves us with C2, plug everything in. We know that A20 led to negative 1 to the 3 minus 2, which is just going to be to 2 there. Trace of B we found earlier, which was 5. Negative 1 times itself is this 1, so we end up with 5. Okay, that makes sense. We get 5 here, we have 5 from our trace. Now let's see how it holds up with our new established property, where trace of B is the sum of its eigenvalues, 1, 1, 3, 1, 1, 3, that equals 5. But remember, the main diagonal elements of B were 2, 1, 2, right? So that being said, the eigenvalues and main diagonal elements did not match, but our traces did. So that's very comforting. Now we see that our last term here in green, C0 had to be the determinant of the characteristic polynomial, and so C0 is the determinant of B, which we found was 3 in A8. Then that leads us directly to, well, here we tried showing that the determinant of B was the product of its eigenvalues, and since we found 1, 1, 3, 1 times 3 gives us 3. Both of these conclude, so we're good to go. That being said, a pretty quick video, but one that was pretty, I would say enlightening because of how much we're going to use this trace and determinant property. So be aware of that. It is coming back again. I'm about to hop on a flight, so I got to run away now. But thanks for watching, and sorry for any background noise. As love you guys. Appreciate all the support and feedback because it's been a very wild year. I'm still recording in the last couple days of December, so appreciate y'all. Happy holidays, or hope you had happy holidays. That being said, you know, stay curious, man. This stuff is really fun. It's only gonna get some sleep, but it'll catch up. Thanks. So, enough of me ranting. As always, thank you for watching, and until next time, stay curious.